Hello, you're welcome back. All right, so let's continue from where we stopped. Now we are going to be looking at the structure of the atom. All right, so now this is a simplified structure of the atom, which here we have the nucleus, and of course, inside the nucleus, okay, inside the nucleus, there are two atomic subparticles, which include the neutron and the proton. Okay, so now it is this these are two atomic subparticles, the mass of these two, that actually constitute the atomic mass of the atom, which we know. The atomic mass of the atom is the number of proton, which is the atomic number, plus the number of neutron. Okay. All right. So now, revolving around the nucleus of the atom at a particular orbit is the electron. All right. So now, proton is positively charged. Electron is negatively charged. Atom is said to be neutral. Atom is neutral because the number of proton is equal to the number of electron. Positively charged proton is equal to the negatively charged electron. Okay, so that is why an atom is said to be neutral. Now let's look at some typical example, okay, of question that you'll be asked concerning atomic structure. Now let's say, of course, this is sodium having atomic mass of 23, and of course 11 as atomic number. So if you are being asked to find the number of neutron that sodium atom have, the number of neutron from this formula is going to be equal to the atomic mass minus the atomic number. So the atomic mass is equal to 23. Then the atomic number is 11. So invariably, the number of neutron of sodium is 12. 12 neutron. 12 neutrons. So please take note of that. Okay, so now, as we said, the charge of electron is equal to the charge of proton, but they are opposite. Electron is positively charged, proton is negatively charged. So approximately, the charge of one electron is 1.6 times 10 raised to power minus 19 coulomb. That simply means that the charge of proton, this is of course for electron it's minus 1.6. So the charge of proton is going to be plus 1.6 times 10 raised to the power of 19 coulomb. So please take note of that. Now, the mass of proton, the mass of proton is very much greater than the mass of electron. Very much greater, right? Greater than the mass of electron. And of course, that is explained, all right, because the proton actually constitutes the atomic subparticles which make up the mass of the atom. I hope that is well understood. Okay. Now, that is what is known as an ion. An ion is an atom with charge, or okay. So when an atom is charged, it is called an ion. So an ion can either be a cation, which of course is positively charged atom. So when atom is positively charged, is cation. And how does atom actually get a positive charge? When an atom loses electron, remember, electron is negatively charged, proton is positively charged. So when an atom loses an electron, then the number of positive charge will be greater than the number of negatively charged particles. So that atom becomes positively charged. Then we now have the anions, okay, which of course is negatively charged. So how do we calculate the charge of an atom? The charge of an atom has charge because there's a difference between the number of protons and the number of neutrons. Okay. So by the time you subtract the number of electrons from the atomic number of the atom, then you can calculate the charge of that atom. For example, if an atom has an atomic number of 11, okay, now it happens that that atom, the number of electrons of the atom is 10. So to calculate the charge of the atom, the charge of the atom is going to be equal to the atomic number, which is the number of protons, minus the number of electrons. Atomic number is 11 and the number of electrons is 10. So such atom has a +1 charge. So please take note of that. Or the question can also be given in this way, in terms of symbol. An atom, okay, Mg2 plus, magnesium ion. Of course, atomic mass is 24. Atomic number is 12. So you'll be asked to calculate the number of electron of the ion. By this formula, to get the number of electron, of course making it the subject of the formula, that's going to be the charge. You're going to be equal to the charge. Please, if I make the number of electron this subject, that's going to be the atomic number minus the charge of the atom. Atomic number is 12. The charge of the atom is +2. That's -2. So at the end of the day, that's going to be 12 minus 2. That is 10 electrons. So that atom will have 10 electrons. I hope that is well understood. All right. Now, let's talk about electronic configuration. We know that electron is actually found at the orbits of the atom, revolving around the atom at a particular energy level. So now we are going to actually describe later on in the video the scientists that actually discovered this as subatomic particles, the electron, the proton, and of course the neutron, and of the atomic model which they develop out of it. But first of all, let's talk about electronic configuration. All right. Now, in writing electronic configuration, or electronic configuration is simply the arrangement of electrons in an atom. Now, in writing electronic configuration, we can actually write it based on principal energy level. If you're looking at principal energy level, which of course is by the symbol N, these are the energy level which is being represented by shells. The lowest is the K shell, okay? L, M, N, O, ... Now, the maximum number of electrons that each shell can take is equal to 2n square, and represent the number for that particular shell. For example, Kerr shell, the maximum number of electrons Kerr shell can take is equal to 2 times 1 raised to the power of 2, which is 2. What of L shell? L shell is the second shell, number 2 shell. That's going to be 2 into 2 raised to the power of 2. That is 2 times 2 raised to the power of 2 is 4. 4 times 2 is 8. That is 8 electrons. Okay, so I hope that is well understood. So, having known that, it is very much easy now to write the electronic configuration based on principal energy level, knowing the maximum number of electrons each energy level can take. Let's look at a typical example. Let's still look at, let me use sodium as an example. Okay, let me use a different element, chlorine. Okay, chlorine have an atomic number of 17, which simply means that the number of electrons is 17. Remember, atomic number of an atom is also equal to the number of electrons. Okay, because an atom is neutral, the number of electrons is equal to the number of protons. So, in principal energy level, the maximum energy level for the Kerr shell is going to be 2. So I'm writing 2. Okay. Now for the Kerr shell, the maximum energy level is 8. So 2, 8. So I have actually written a total of 10. Then I'm left with 7. Now that 7 will go to the outermost shell. That simply means that chlorine has 3 shells. And this is the configuration. Okay. Or in some textbook, it can be written in terms of the power of the alphabet of the shell. Can write it this way. Okay. Raised to the power of 2. Okay. Then of course L raised to the power of 8. M raised to the power of 7. Okay. So it can be written that way. I hope that is well understood. Please take note of that. Now, sometimes you might be asked to write the electronic configuration of an ion. For example, sodium ion. Now, if you are asked to write the electronic configuration of an ion, now this ion, this is +1. +1 simply means that this atom have lost 1 electron. Remember, an atom gets charged by losing an electron. An atom becomes positively charged by losing an electron, and of course it becomes negatively charged by gaining an electron. So this atom have lost 1 electron for it to become +1. If it was +2, it means it has lost 2 electrons. So initially the electron of the number of electrons is equal to the number of protons, which is 11. But because it's +1, that simply means that the number of electron of this sodium atom or sodium ion is 10. So writing the electronic configuration, I have to, of course, 8 to complete the 10. Okay. So please take note of this. All right. So now let's look at another way of writing electronic configuration. Now, this principal energy level of writing an electronic configuration is also known as the principal quantum number. So let's look at the another way known as suborbital levels. Okay. Of course, in terms of quantum number, we call this the subsidiary quantum number. All right. So in this case, we have 3 orbitals, x, p, d, and f. Now, the symbol we use for the subsidiary quantum number is L. So for x orbital, all right, the L is equal to 0. The L starts from 0. Here L is equal to 2, equal to 1, please pardon me. For P, for D, L is equal to 2. And of course, now the maximum number of the orbitals, the number of orbitals for X is 1. The number of orbital for P is 3 orbitals. The number of orbitals for D is 10. Okay? And of course, F is 14. Now that is, by the way, we are going to talk about the orbital diagram. Now let's write the electronic configuration. Now to write the electronic configuration based on the subsidiary quantum number, we arrange the orbitals and of course the shells this way in ascending order. Okay, we have 1s2, 2x2, 3x2, 4x2, 5x2. Then I now move to the P. Starting P, I'll have to start with 2. From 2, energy level 2, P raised to the power of 6. Now this 2 is the maximum number of electrons. S can actually take. X has 1 orbital. In each orbital, the maximum number of electrons is 2. So since P has 3 orbitals, each orbital takes a maximum of 2. So there are 3 of them, that is going to be 6. So please don't forget. Two P, 3p6, 4p6. Okay. Let's continue. Okay, so I have 3d10, so on and so forth. So let's look at this. So if you want to pick our electronic configuration, we pick it diagonally until we have the maximum number of electrons for that atom. For example, from this arrangement, if I want to write the electronic configuration of chlorine, which of course have electron or 17 electron, I will pick 1x2. Then the next I'm going to pick 2x2. Next I'm going to pick 2p6. So total is total that I have so far is 10. I'll continue. I'll pick 3x2. Total is 12. So I'm left with 4. Okay, everything is 17. So I'm left with 5. So I have to go again diagonally. So now, so this is gonna be 3p. Won't be up to 6, 5 to complete. So please take note of that. Take note of that. What of magnesium? 12. 12 electron. I have 1x2, 2x2, that's 4 so far, 2p6, that's 10, then left with 2, That's going to be 3s2. I hope that is well understood. So you can actually write for other elements. Okay, now there is one I need to talk about. So this has to do with, is based on orbital diagram. Now, if we are to write electronic configuration in orbital diagram, we use boxes to represent each orbital. For example, let me write the electronic configuration of sodium, which of course is 1s2, 2x2, 2p6, that is 10, then 3x1. So each of these, for 1x, you know, x has an orbital. X orbital is just one orbital. For 2x, still one orbital. P, 2p, p has 3 orbital. Then finally x, 1 orbital. So let's start filling the electron. For 1x, okay, the electron will have opposite spin, one upward, of course, one just half arrow. This is this represents 1x. For 2x, 2x2, up, then down. Then of course for p, the whole of this is p. Okay, which of course an orbital, that is, you have p, px, py, pz. 3 orbital, px, py, pz. Okay, so the whole of this please pardon me. Okay, so now let's look at that. So the whole of this is for 2p6. Now in filling this orbital that is more than 1, first of all, according to Hund's rule, you fill it singly first before you now pay it. This 1, 2, 3. So I'm left with 3. You now pay. Alright, then for x, I just left with 1. So this is the orbital diagram of writing the electronic configuration. So from this orbital diagram, now we can see that sodium has one unpaired electron. That is singly filled electron. So when you draw the orbital diagram, you'll be able to know the number of unpaired electron in orbitals, in an orbital. I hope that is well understood. Okay. Alright, so far so good. I think I've actually done okay enough for this video. Okay, so okay, we're going to continue in the next video. So see you in the next video. Thank you very much.